Welcome to the Rocky Mountain AI Interest Group. The following presentation, entitled Fine-Tuning and Optimizing Large Language Models, took place on January 10, 2024, at the Atlas Building on the CU Boulder campus.
So now I want to introduce to you Mark Hennings. Well, actually, you've got your mic there too. He's the founder of Entry Point AI, a modern platform for fine-tuning large language models. He's a serial entrepreneur, and if you ask him, I got to find out some of the things he has started, which are creative and interesting and fun. One of which, Inc. 500 alumni, and he's a self-taught developer. So that's a lot of us in the room, which is exciting to have him here. But he's also passionate about democratizing AI, and I think that's a big, exciting element to our group. And what we're all amplifying is really looking at the ethics and how we can democratize this globally. So put your hands together for Mark Hennings. Hennings.
I'm super excited to be here. I've got a pretty big presentation plan. I'm going to try to cover a lot of ground because it's a big topic and I think it deserves it. So we're going to be talking about optimizing and fine-tuning large language models. Essentially, how you can apply different techniques to work with large language models to get better results. So we're going to talk about how to improve the usefulness, the accuracy, and the relevance of outputs, reduce hallucinations. I put it in quotes because it's kind of a feature of large language model. That's really all they do is hallucinate because they're not really connected to the real world. But we'll reduce the ones that we don't want to see as much. We'll also try to prevent harmful or embarrassing outputs from our large language models. Unfortunately, there are a lot of ways this can happen, especially when you're doing something super broad using these generalist chat-based models that really have the potential to output anything. We'll dive into that. Toxic bias, unethical, illegal content, and prompt injections. There's ways to mitigate these things. We will look to extend the capabilities of large language models. As a self-taught developer, I'm very passionate about connecting traditional software to large language models. We don't have to throw out all of our existing tools just because we have something really new, cool, and shiny that we can work with. Also, don't try to make large language models do things that they're not good at, which there are plenty. So, and we'll try to think about ways to do all this faster and cheaper as well, which primarily comes down to choosing the right size model for the task, at least at the level we're looking at things. I'm not going to be diving super deep into anything too low level. I'm going to be kind of zooming in and out. I'm going to be explaining the terminology that you see in machine learning that can really trip people up. It's not as hard as it sounds. So let's cover prompt engineering. We're going to cover a lot, okay? Prompt engineering, just briefly, we're going to breeze through it because I think we all have heard enough about this last year. And inference parameters, how you can make some tweaks there to potentially get better outputs. Retrieval-Augmented Generation is a really big one. Function calling, I'm going to talk about how that actually works. Of course, OpenAI has an API for it, or a feature for it, but I'll explain how it actually works. And then, of course, fine-tuning is what Entry Point AI, my software platform for fine-tuning, that's what we do. That's what I'm really passionate about. I'm passionate about all these things, and we'll just kind of cap it off with fine-tuning. So some underlying or guiding principles you can keep in mind as we're going through all this. First of all, is you have to break down complex tasks into multiple steps. The biggest mistake you can make is to take a large language model and just try to make it do everything for you in one big step. I think that's where you'll be the least optimized. I mean, go ahead and try it, right? Like maybe it'll work, maybe you're fine. But in general, we need to break things down, and then some of it will go toward traditional software tools, and some of it will, fall onto a large language model or maybe a series of models. The second is just use traditional software approaches when you can. So we'll look at some charts that put these things together. So let's start with prompt engineering. With prompt engineering, there's some interchangeable terms. These will be useful throughout the presentation. You can use the term prompt. That's cool. Input, same thing. Context window, just feeling a little technical, okay? But essentially, the context window is your prompt, and it grows as you start to add tokens to it in the completion. Context window length would be more specifically the maximum length of your context window. So prompt engineering, typically what you'll see is something like some priming, okay? You're a plumbing Q&A bot that answers questions about plumbing in a helpful way. I want you to use 10th grade language and explain things in a simple way that anyone can understand. So that's like the style and tone. This can get quite extensive in terms of your instructions. You need to handle errors and edge cases. So like I'm trying to make a plumbing bot. I don't want you to answer questions about like interior design or something like that. So just don't do it, okay? And then you'll see, you'll want some kind of a response from it that you can use in your application. JSON is kind of the language of the web. So it's typically what we go to. So that's the system prompt, and the user prompt, I'll explain these more, but the user prompt was then the user inquiry to your prompt here. So somebody comes and says, how do I fix a leaky faucet? I like to call this the dynamic content, because if you think about your whole prompt, most of it's not changing from each time you call the large language model. The only thing that's really changing is this dynamic content. It doesn't have to be a question, but this is a Q&A bot example. It could be tons of different things. I think last year, like a lot of people were just focused on chatbots because it's new and exciting and it's this big thing and they can do so much. I'm personally more passionate about much smaller, like little specialized use cases that I'll talk about. And to make these better, you go on the internet and you find all kinds of prompt hacks. Like, I'll give you $200. You do a good job. Please, this is very important. I saw this in a Microsoft GitHub repository just yesterday, and this just made me laugh. Take a deep breath, and then the prompt, or ending with "to be consumed by an application" is supposed to make it more likely to put out JSON. And I would say, hey, just try it. If it works, that's fantastic. Evaluate it. But I hope all of this stuff goes away, because I think it's taken advantage of the bias in the training data that we're training these on. And if we're really training them better and we have better architectures, they shouldn't be necessary in the long term, in my opinion. But we are working with what we have. So go for it. I think these hacks will only get you so far. And in this presentation, I hope to show you some more robust ways to get results from large language models. In terms of practical things you can do to improve your prompt engineering, I think the first one is to just make sure you're using the system and the user prompt appropriately. So when a model is fine-tuned to become a chat-based model, it's typically given some special syntax, which includes these special tokens that you cannot insert through your own text inputs. And so they're sort of protected in a way. And it's trained to distinguish the stuff that's in the system prompt at the beginning from the stuff that's in the user prompt that maybe is the system prompt is trusted inputs. So as the administrator of this large language model, you have some data that you trust. Maybe it's metadata about a customer. Maybe it's your instructions, your prompt. Put it in the system prompt. And then there's untrusted inputs. So if we have a web application facing users, those users can come and ask questions. They can try malicious things. They can try to hijack the prompt. That's an untrusted input. It could be anything. So to make sure to put that in the user prompt. And over time, as the training gets better, the large language models should be able to distinguish better between these things and hopefully improve issues like prompt hijacking or prompt injection when somebody tries to get your model to do something that you really didn't intend for it to do. There's also few-shot learning. If you're not familiar with this, essentially, you can really boost your prompt by including some prompt or some pair of examples, like how to fix a leaky faucet, and then include some examples of that and other plumbing-related questions and how you want your bot to answer. So this is starting to go in the direction of show, not tell, which we'll really focus in on when we get to fine-tuning. But 3+ examples is a really good starting point. And then chain of thought is another really useful technique. I find it personally annoying when I'm using ChatGPT, and I know that's what it's doing. It's just trying to reason through it before it actually gives me the thing I wanted. But it does help the large language model, because as it's reasoning, that gets put back in. This is an iterative process I'm going to show you. But it gets put back in, and so it can use its own reasoning to help it get to the final step. It's just that you have to make sure it reasons through it before answering. If you ask it to justify its answer afterward, it's not actually improving the answer because it already just jumped to a conclusion. So that's the section on prompt engineering. And inference is a really scary word, okay? But it just means that point when the model starts generating text. So these are interchangeable terms. You can say inference, generation, prediction, completion, or completing. It's all good. Use them all right? A couple other interchangeable words, if you're not familiar, token and word. Basically, the models will generate sections of words at a time, but for the purpose of describing how they work, it's okay to just say they generate one word at a time, even if it's generating like the prefix and then the end of the word and the ing and then the punctuation. Okay, so inference is when it's predicting the next token in a loop. The way this works is that you give the model a prompt. A long time ago in a galaxy, you just want to say it, right? Okay, then the model does a bunch of math. It does embeddings, attention, and linear algebra, and I'm not going to get into that. But there's math, okay, equations. And then the output from that process is a list of tokens or words. Let's say it's in descending order of probability. So the most likely one is at the top. Then the model is going to select a token. So it's got a list of words. There's a most likely one. And then the selection part or the sampling of the token is where almost all of the parameters kick in for how you can affect what word it will choose and how the model behaves during inference. You have temperature, top P, top K, frequency and repetition penalties, and then you can even do granular individual biases for specific tokens. So you can say, never output these tokens. Like, I hate the word rug. Never use the word rug. Or, for a classifier type of model, if you only wanted to output 5 different possible types of words, you can say 100% for these, 0% for everything else. So then you've selected a token and you get the word far. Perfect. The next step is, do we stop? And that could happen in 2 ways. You either hit the maximum length that you specified for it to generate, or it shows the stop token, which is a special token that it chooses, and then it knows to stop. If it did not choose the stop token or hit the max length, it goes back and it does the math all over again. It uses the new prompt, and it does that in a loop, okay? And then finally, you get a completion, which is far, far away. And the prompt plus the completion is the context window. What a lot of people don't know is that almost all of this is completely deterministic. This math that happens inside the model architecture is not random, okay? You get the same list of tokens out every time. But depending on how you set your parameters, you can optionally make it random. So this is typically done through the temperature parameter. And if you set temperature to 0, you get the same result from a large language model every time. So here's how I'd recommend setting temperature. This is like the #1 parameter that I like to set. I often set it to 0. So I like to set it to 0 for classifiers where I want really specific predefined outputs. For evals, because then it's reproducible outputs, you'll get the same test results every time from your examples. Or when there's strict output formatting requirements. When we talk about making a large language model do too much at a time, it's a lot to ask it to be creative and to adhere to something strict, like this has to be in JSON output, because that's a strict requirement. Like, if you wanted to choose the right curly bracket at the end for your JSON, you don't really want a high temperature that might make it choose a random different token or character that leads to invalid JSON. You should set it higher when you're looking for creative outputs. I still try to stay under 0.7 is just my rule of thumb. Or if you want longer outputs, I've just found that they tend to run on longer when you set the temperature higher. So, and remember, there's a thin line between creativity and madness in humans or in LLMs as in humans. So now we're going to move on to Retrieval-Augmented Generation, or RAG, as I will refer to it here. And in RAG, let's take that system prompt and user prompt we were working with earlier. How do I fix a leaky faucet? Well, we're adding this knowledge to the prompt. And the knowledge, wouldn't it be great if we just could give our prompt the information about how to fix a leaky faucet? Because I have this stack of plumber's handbooks, in the corner. So can we just pull in the appropriate chapter and section from that handbook? So that's what we're doing. That's what we're trying to achieve with RAG, is inserting knowledge that will help with the inquiry. In order to do that, or the reason to do that is because large language models don't store facts, they store probabilities. So we shouldn't be trying to treat a large language model as a database. The database is not a large language model. It's hard to get, it's obviously possible to get the exact training data out of large language models in specific situations, but in general, it all gets sliced and diced up. And if you have discrete facts that you need to be utilizing in your application, then it's best to provide it to the model. So here's how this works. You start with a corpus of text. Some web pages, PDFs, stack of plumber's handbooks. And you're going to somehow chunk those up into meaningful sections. Like, okay, a chapter of a book is meaningful, maybe a few paragraphs. You don't want to end it in the middle of a sentence. Things like that. You're trying to find some meaningful text that if you inserted it into a prompt, it would help your model perform better. Then you're going to convert it into an embedding. So an embedding is the vector representation of text. It's a series of numbers. Okay, that's all you need to know. It's a lot of numbers. And if you take some text and you use a model, so you actually use you use a language model, some kind of model, to convert it into an embedding, some kind of embeddings model, you get the same embeddings at a time. And then you can store that in the database along with the chunk of text that you started with. Then you have this database and you have these embeddings. An inquiry comes in, how do I fix a leaky faucet? You're going to convert how do I fix a leaky faucet using the same embeddings model into this sequence of numbers. And then there's this cool thing. Once you have your words in number form, you can compare their similarity. So you can actually search your database for the most similar text to what the user inquiry was. Then you have these 3 to 5 results, let's say. You build your prompt again, but this time you have the inquiry and the information you retrieved from your database. Then you generate. Ta-da! It's so easy. Why isn't everybody doing this? GPTs do this, by the way, for you. So that's cool. But this is where it gets hard, because the hard part is making sure that the information you retrieved is actually the right information. And there's a lot of optimization that has to happen in order for that to go well. So certain optimizations you can do to the process is you pre-process that inquiry. Maybe you strip out all the unnecessary fluff that could be in there that's not really relevant to what your database has in it. So you summarize it into just fix leaky faucet. Then you do the same thing we talked about. You search your database, you get some results. But instead of just assuming those results are good, you ask another LLM, which of these results is most applicable to the inquiry that came in? And then hopefully you get some better information. You can build your prompt and generate it. And then at that point, you could also self-reflect and say to another LLM or the same LLM, whatever you're using, a fine-tuned model perhaps, is this a good and accurate output? Like, should we really return this to the user? If not, rewrite it and give it one final chance to correct its work. Okay. So the devil is in the details with a RAG flow. But there are a lot of benefits if you can get it right. You can reduce hallucination by grounding the model with trusted data. That means you're really giving it hard facts inside the context window that you believe to be true. And since models are very sensitive to information that's in the context window, it makes RAG very powerful. It's just hard to get. It's just hard to dial in. You can get the 90% great results for demos, and then the last 10% you'll just spend the rest of your year working on. It also allows you to reference knowledge from outside the model's training. So, at this point, most people aren't retraining a model every single day when certain news articles come out. So, if you have a real-time feed of news or tweets, I think that Grok references real-time tweets using RAG or something like that. So you can reference real-time knowledge that the model wasn't trained on. It allows you to utilize proprietary data and mention of recent events and kind of keep your model up to date depending on where your data is coming from. Whew, we did it. Three parts in. Part 4, function calling. Has anybody tried function calling on OpenAI? All right, cool. So function calling is having a large language model decide what data is needed or what action to take. I was just looking at the OpenAI API today, and I think they deprecated the function call terminology, and they're calling it tools now. I think that's maybe more intuitive. Also, I looked at their documentation for it, and in an API call, you can describe functions and have the model intelligently choose. So we're having a large language model make a decision for us. And then it calls the function in your code. So I think they probably had a lot of people that were confused and thought the large language model was just this autonomous agent that could go out on the internet and do things for them, which is not true. We are not there. Here's how it works. So in one scenario, it's kind of like RAG with a router. You start with a user inquiry. Let's say, what's the weather in Boulder right now? Now you have a model, which could be a fine-tuned model. It could be something you're using with a prompt, a chat-based model. And you ask it to recommend one or more of your predefined functions. So you have to know in advance what functions you're going to support. And by functions, I mean, like what tools, what actions can this take? So I want my model to be able to get the weather for people. That's very important to me. So I told my model that it can choose to get the weather if somebody asks about the weather. And so it would return in some kind of a JSON format, basically the name of the function and any parameters it needs. We're just assuming right now that we're not going to go back and ask the user like additional questions. So we're just keeping it simple and making some assumptions so that we can provide parameters for our function, like the current time and the location, Boulder, Colorado. I'm assuming it's Colorado. The model is going to assume that. And then our system is responsible for actually calling the function. So we run some kind of a get weather call, which could be like an API call. Let's say AccuWeather. Maybe we are AccuWeather, so we just search our database for the latest weather. Oh, it's sunny and 72. Great. Now in the code, we know it's sunny and 72. We assemble the prompt, so we combine the user inquiry, the actual weather report, and your instructions into the prompt. And then we get a beautiful generation back. Oh, gee, it's so nice and bold right now. The weather is sunny and 72. Perfect time to hit the trail. So that's retrieving knowledge with function calling. Of course, you can also do things in the real world with function calling, or more exciting things, perhaps. So user inquiry comes in like, I'd like to order a pizza. Don't ask me any questions, just do it. And then so we have full license to go ahead and say, we have a function called order DoorDash, which we decided we were gonna, we're like supporting this function. Maybe we have like a list of 20 functions and order DoorDash is one of them. We're gonna order a pepperoni pizza from any restaurant, the closest one, and use the address and card on file to keep it simple. And then we call the function the DoorDash API, and it tells us, great, delivery time is in 30 minutes. So now we can respond to the user. Downside of this, by the way, is you have to wait for all of this stuff to happen, which is another problem. But we combine the user inquiry, the pizza API response, and your instructions into a prompt. I ordered you a pepperoni pizza from the nearest pizza place on DoorDash. Should be there in 30 minutes. Wish I could enjoy it with you. Aw. So you can do a lot of things with function calling. You can fetch data from an API. You can find out how long a drive will take in current traffic, search the web, perform math, give your LLM agent or application agent-like capabilities, right? Send a message, add a reminder, order groceries, anything you can do with an API, which is quite extensive. So I would think of this like anything Alexa can do, you could build an LLM router that can choose to do that. The downside is you have to support all those functions that you want to offer. So it's extremely powerful because it allows you to connect to any API or resource, which also means we have to be careful about how we use it and what kind of abilities we expose to people, because the large language model is making all these decisions about the parameters. Theoretically, you could make one that just writes any code you want and executes it. And I think I saw at the OpenAI Dev Day, they did that. And I was like, oh my gosh, I'd never do that in my application because I would not trust it. And prompt injection then becomes a major, major concern. But there's still a lot you can do. And now we are in the final section, which is fine-tuning. And fine-tuning is training a model on more data. So you're going to start with the data that's been trained to some point, and you're just going to give it more data. We're actually changing the weights of the model. So there's interchangeable terms here. There's actually a lot for this one. Fine-tuning, training, teaching, learning, adaptation, alignment tend to be the ones in the scientific paper, adaptation, alignment, scientific papers. But you can think of these all as, oh, okay, there's nuances potentially depending on the context, but don't get thrown off if I use them interchangeably. So we're changing the weights of the model. A model has a bunch of numbers in it, like a 7 billion parameter model. Parameter is the same as weight, is the same as number. So they're just numbers. And these numbers are what calculate the probability of the next token. And when we change them, we change the behavior of the model. So here's how a large language model is actually created. The first step is pre-training. We take a giant amount of text, like 2 trillion tokens for Llama 2. And then we train it on that. It doesn't really get like, this is right or wrong. We just give it text and it digests it and it learns to predict words. Everything after that is fine tuning. So we do instruct tuning, which is how we get chat-based models. And this is really incredible that we can even do that, I think. It's like you just train a model on a ton of text and then all of a sudden you can give it a little additional data and it'll talk to you. It's really crazy to me. I'll emphasize that again in a minute. From there, we typically, not always, do safety tuning. And then there's also this, so safety tuning is going to try to prevent it from outputting really, really nasty stuff, things you don't want it saying to people. And then there's also domain tuning, which is more experimental. This is where you are then trying to give it maybe additional data in a specific field like law, medicine, finance, education, and seeing if you can get it to do a better job. I'm not totally aware of any super successful results of that. Google MedPalm 2 is a prominent example, but Microsoft is like throwing shade at them, saying they can just engineer a prompt that does better with GPT-4. It's kind of in flux right now. But then, and this is where I spend a lot of my time, is task tuning, which is at any of these stages, then you take one of the models that's been trained and you turn it into a task specialist for your business or for your whatever you need it for. And a task specialist would be like, I want to write blog articles or press releases or qualify sales leads or something very, very specific. There's a subset of what it could do originally, but now I want it to be very good at this specialized task. Some fundamentals to understand about it are that it's a type of supervised learning. So supervised learning is this fancy term that just means you're giving it a right answer. So there's an input and then there's a pair with that is good. And that's what you want it to learn to output when it sees the input. it's a type of transfer learning. So you're starting with a model that's already been trained. And it's become much more accessible due to parameter-efficient fine-tuning methods. This includes QLoRa, which is quantized low-rank adaptation, which actually allows you to do fine-tuning on consumer-grade GPUs. So pre-training might be done on a huge cluster of 5,000 GPUs, and I can take that base model that they spent millions of dollars on, and I can spend a couple dollars and just fine-tune it at home on a 24 gig GPU that I have sitting around, which I don't, but I could. Fine-tuning also limits the scope of what a model will do. Mark, why are you telling us about limiting the scope? We want it to do everything. Well, the benefit of this is it increases the predictability of model behavior. And at the same time, it also degrades performance for other tasks, which is a feature, not a bug, because you actually don't want your models to do everything. Like we talked about at the beginning, there are a lot of things that you don't want them to output, like safety tuning. We're teaching it not to output certain things. So I can fine-tune a model that will only output like very high, high, medium, low, very low to qualify a sales lead. It's not going to go off and do something very, very upsetting. So here's an example of what instruct tuning actually does to a model. So I took this prompt the other day, tell me how to cook a steak. And I tried it on the Llama 2 13 billion parameter base model, which has not been instruct tuned. It's just raw, straight out of pre-training. And it said, the problem with the world is that intelligent people are full of doubts while the stupid ones are full of confidence. Charles Bukowski. I expected it to give me something kind of off the rails that was further than I expected. And the strangest part about it is that I cannot for the life of me get models to usually give me real quotes from real people when I ask them to, but this appears to be a real quote. I took the same prompt and went to the chat-tuned version of the same model, and it said, oh my gosh, I'd be happy to help. Cook, and it gave me instructions. So there's a huge difference between these two, a vastly huge difference in what you can get out of the model. Okay, this one's not very useful to me, except for the presentation. Safety tuning is also important. I took this prompt. I asked for research purposes, and I wanted to be very explicit. Like, I want to do this illegally, okay? How do I illegally enrich weapons-grade uranium from home? And I went to the Llama 2 13 billion chat model that we already tried with the steak, which is notoriously kind of like overt safety tuned, or it's very conservative. As a responsible and law-abiding AI language model, I cannot provide information. And also, it's very concerned about the environment for this particular task. So I took the same prompt, and Mistral 7B instruct has no safety tuning. And it was happy to help me. There are no moral qualms in large language models unless you safety tune them.
Did it provide steps?
Yes.
Wow.
Yeah. Absolutely. I had to cut it off because I was like, no one's gonna read all this. But
they were.
You know, I'll get back. Yeah. I'll follow up on that item. So then task tuning is very much more specialized. So let's say we take a chat model and we want to create a support ticket classifier. This is a common problem. Let's say I'm a business and I get a lot of support tickets and I just have one layer of support people and I'm just kind of round robin assigning these support tickets as they come in. Well, and we're growing and like I know some support people are better than others. I want to have a higher tier of support and a regular tier, and I want to offer higher tier support for important clients. So I can fine tune or task tune a support ticket classifier on my data, my company data, my examples of support tickets that have come in and how high we rank them in terms of priority. So let's say T-Mobile writes in, we are experiencing a service outage. This is affecting our telecom network. This sounds serious. We need hourly updates per our SLA. My classifier can output one word, high. It's high priority, and it can be immediately routed to top tier support. Initech writes in, hey, I have a quick question about how to adjust the report format on the dashboard. TPS reports seem to be missing cover pages, and I can immediately route that to the lower tier support, low priority. So that's one practical way to think of fine-tuning a classifier for a simple business application. You can also use classifiers as part of some of your LLM flows for that self-review step we talked about. Let's say I want to create an AI model that's going to, maybe I'm WebMD. Okay, so I'm going to replace some stuff, and we're going to have a bot that will just suggest what might be what's ailing you. And you provide a list of symptoms, and we say, that's a broken arm. So our quality check model that's been fine-tuned on a lot of symptoms, and then what is the probable or potential diagnosis would say fail. And then we could go back with that information, and we could say, hey, it is not a broken arm, but these are the symptoms. Can you try again? And we could maybe get a better output, a more likely output that would pass our quality check layer. So in general, fine-tuning shows large language models how we want to apply knowledge. And it has a lot of benefits if you're able to do it right. My favorite benefit is not immediately obvious, but fine-tuning is show, not tell. Prompt engineering, you're telling the model. You have to tell it everything you want to do. If you don't tell it to do something, it's not going to do that. We're just going to do something else. With fine-tuning, you're teaching it by giving it prompt completion pairs. So let's say someone is the best writer in the world, and I ask them, like, what are the 10 to 50 things I could just do to write as well as you? Okay, they might be able to tell you and describe those 50 things, but you can't just like learn intuition that way. But these models have this incredible, powerful learning ability when we give them examples. And even if I can't explain why it's good, it'll probably learn it, or at least learn enough to imitate it. So it's a really cool way, it's a really different way to work with getting results from models. Fine-tuning bakes in the style, tone, and formatting to your outputs. It narrows the range of possible outputs. You can train smaller models to perform at a higher level, allowing you to perform tasks cheaper and faster, which can be very significant in terms of cost savings and speed. I would also argue that it's a better workflow for teams because a layer of training data, you can have as much training data as you need. And when you need to add functionality or cover edge cases, you can add examples to your training data, which are like separate examples versus having to go in and everybody tweak one prompt. And it also reserves a context window for the most relevant and dynamic content. Like that dynamic content I showed earlier, how to fix a leaky faucet, right? It's like, instead of having all the boilerplate before that, we could just have the dynamic content, or at least more focused on that. And you might say, like, why? Like, why would you want to do that? I mean, tokens are cheap, right? Well, the real reason is that large language models tend to lose focus when you give them too much. There's this paper that I really, really like called Lost in the Middle, how large language models use long context. And it shows a chart where on the x-axis, as you give it more documents, the accuracy starts to go down in its ability to find a specific fact from the documents. And they state, we observe that performance is often highest when relevant information occurs at the beginning or end of the input context, and significantly degrades when models must access relevant information in the middle of long context. So sort of like people, we see the thing at the beginning of the list and the end of the list, and we kind of ignore everything in the middle. And maybe that's because it's been trained on human data. Maybe it's part of the architecture. I don't have an answer for why. And the paper didn't necessarily either. But the fact is that order matters in your prompt, especially as it gets longer. And the general principle I'm trying to get at is that the less boilerplate you have to stuff in your prompt, the more you can help the large language model focus on the things that you actually want it to pay attention to. Okay, so can we add new knowledge with fine-tuning? And I would say maybe, but fine-tuning works much better to teach patterns than facts, patterns of behavior. And here's why that probably is. If you squint really hard on some screens, you can see a line for the instruct tuning here, but this is the difference in the amount of data that is being fed. So if Llama 2 is trained on 2 trillion tokens, in the paper they said they annotated 27,540 examples for instruct tuning. And I just took half of the max context length, said 2,048 tokens each. That's 56.4 million tokens. And that's what I'm comparing in this pie chart. So there's way more pre-training than fine-tuning in terms of the data that it's digesting. And this other paper that I really like, called Less is More for Alignment, has the superficial alignment hypothesis. We hypothesize that alignment, remember that's fine-tuning, can be a simple process where the model learns the style or format for interacting with users to expose the knowledge and capabilities that were already acquired during pre-training. So what we're really doing is just unlocking the things that it already learned with most of the fine-tuning. Even with the chat instruct tuning with 27,000 examples there that they trained it on, it's like, you didn't really teach it how to talk. I mean, you teach it how to be conversational. You shifted the parameters of the model just enough that it became conversational. But essentially everything that it knows, everything that it's telling you was learned from pre-training. Other things that are just amazing from this paper is that they fine-tuned a chat model that rivaled GPT-3 on a highly curated data set of just 1,000 examples. So Llama 2, 27,000, they're saying, hey, we got really far with 1,000 examples. And the reason, and like most previous data sets were 20,000 plus, you can find plenty of places where it's like 400,000 plus examples to do a chat model. But it's coming way, way, way down, especially with papers like this, where they are emphasizing that they were able to achieve this success with input diversity and output quality. So very different inputs and then really, really high quality outputs. The scientists themselves actually worked on the data set, okay, making sure that it was a very, very high tier. And then it wasn't that great at multi-turn dialogue. This is when the user says something, the LLM responds, you feed that back in, the user says something again, and it's supposed to kind of follow like person A, person B, person A, person B. A mere 30 examples made significant strides in its ability to handle multi-turn dialogue. And when it came time to being able to do bullet point lists and other more complex formatting tasks in response, they were able to actually add just 6 examples, and it unlocked this ability, which I think is just incredible. So how much data do you need to task tune? I want to create a very specialized task LLM for my business that does this one thing really, really well. You just need a few dozen examples for behavioral change. I do this all the time. And the data set is not like a limiting factor, I think, for businesses. As much as it seems out when you go out there and like try to learn about fine tuning anyway, because a lot of the information is outdated. It's based on architectures that aren't as good as the ones we have now. But there's also a few things that fine tuning is not. It's not an easy way to store new information in a model. Like think about that chart. It's like, hey, it was trained on all this data. Now I want to teach it a bunch of information or change some of the things it was taught. That is hard to do. It's not something only data scientists can do. And it's not very expensive. Most of the fine tunes that I run are like 20 cents to $1. So, and Stanford trained the Alpaca model, which is a Llama 2 chat model for less than $600. And they used a bunch of data on that. So So to cap things off here, I want to do an overview of the kind of the top 3 techniques: prompt engineering, RAG, and fine tuning. Prompt engineering is great because it's easy to work with. You can do rapid prototyping. It's super intuitive. RAG is incredible because you can connect external data sources. You can put dynamic knowledge in the prompt, and you can get real-time information. Both prompt engineering and RAG are limited to the context window. Fine-tuning narrows the model's behavior, gives you more predictable outputs, and bakes in the style, tone, and format. Prompt engineering and fine-tuning both steer the behavior of the model, and RAG and fine-tuning both apply data and domain knowledge, but they all give you better outputs. So it's really not a question of which one should I do, but when. At Entry Point, we are a modern platform for fine-tuning large language models, no code required. We do a fine-tuning masterclass at least once a month. It's totally free, and you can actually fine-tune your first models, so you can, see if it's really possible or not. So I saw a few skeptical faces, but I assure you that it is, and it's not as hard as it sounds. So, yeah, thanks so much.